Well, 17 degrees in February. It's not bad, is it? I had a note from somebody, newcomer actually, to ham radio, and asked me about inverted V antennas. What's the difference between an inverted V dipole and a horizontal dipole? Well, it's an interesting question. I thought it's something I haven't covered, I don't think. I'm not sure whether I have covered it ever, but anyway, I thought this is time to actually look at the inverted V dipole because it's got quite a few advantages and not that many disadvantages. So let's take a look at the inverted V dipole for the newcomer.
Hello and welcome once again to the Waters and Stanton video channel. Before I start talking about the inverted V, let me just tell you a change on our website if you haven't actually noticed it already. We have now got a blog on our website. There's a link top left of our website which links you to our new blog. Now this new blog actually is a summary, a textual summary of the videos I do. If you go onto the blog and have a look there, you'll see in text a concise summary of each video. It may be quite interesting to have a quick look and just see the content of the videos that we do before you watch it, or perhaps after, just to refresh your memory. So we've got a new blog, check it out, front page of our website. This video is going to be about inverted V dipoles. But before we talk about inverted V dipoles, let's just take a look at the dipole, because the basic dipole is the basis of many ham radio HF antennas and VHF antennas. We're going to confine this to HF operation, the inverted V. So dipole. The dipole is a simple antenna. It's two poles. It's a horizontal wire. It's got a left and a right side to it, broken in the middle and fed normally with coax cable. You can feed it with open wire feeder, but we're going to confine this to coax fed dipoles.
So let's take a look at the basic dipole. There's the two legs. To find out the actual length, the physical length of that dipole, we take a figure of 4, 6, 8. We divide that by the frequency in megahertz. And if, for example, we were operating on the 20 metre band, that would give us a result of 33 and a bit feet. Now, I have to apologise, I work in feet. I've always worked in feet and I continue to work in feet. You can change that formula for metric, but anyway, I'm going to work in feet because that's something I've been brought up on. So 468 divided by 14 megahertz gives you 33 and a bit feet. So in other words, a half-wave dipole is that length. And we feed that with coax cable. We could take the shielding to one side and the inner conductor to the other side. And that works, but purists would say, well, you've got a balanced antenna and you're feeding it with unbalanced cable. You need some sort of balun. It's very easy to put a balun in there, but really and truly, the simple solution is actually to wind some of your coax cable at the feed point there round a ferrite toroid. Ferrite toroid is like that. And you just wind some of the coax cable round that toroid like that, and then take the cable up to the antenna. So your coax cable has got an inner conductor there, got the outer conductor there, the shield goes to one side and the inner conductor goes to the other side of the antenna, and then you've got your ferrite toroid there wound with cable, I would say probably about 7 or 8 turns, and that will act as a balun and a line isolator. And then you'll get a good connection to your antenna and you won't have any problems at all in terms of the balance to unbalanced.
So the dipole is a very simple antenna. It's basically a single band antenna. It will operate on odd harmonics, but what actually happens is the harmonics are not directly related to the fundamental. They tend to be higher in frequency. you could operate a 40 metre dipole on the 50 metre band, because the third harmonic is 50 metre band or 21 megahertz, but you'll find that the frequency of resonance on 21 megs is very high. It's probably outside the band. So for all practical purposes, we regard the dipole, the simple dipole we've described, as a single band antenna. You can have trapped dipoles, and what we're going to talk about now with the inverted V will also translate into trapped dipoles.
By the way, a trapped dipole looks something like this. You've got the leg with the trap in there, and a bit more wire that way, and similar this side. Those traps will enable it to be multi-banded, operate on several bands. What you can have, of course, to get rid of those traps there, you can have balanced line, open wire feeder, G5RV. They all translate, or can be translated, into inverted V antennas. Now, the inverted V does have one big advantage, and that is that it basically only requires one central support. So we'll have a support mast there, and we'll have our antenna coming down like that in an inverted V. That makes it very simple. If you're using a metal mast and you're feeding it with coax cable, then there's no problem. If you happen to be using balanced line, as you would with a G5RV or a conventional doublet, then what you can do is you can actually feed it off center. So we have a metal mast there, and we feed the antenna slightly off center. The balance line comes down like that, and the inverted V goes on like that. The space in between that can be around about 2 or 3 feet. It makes no difference at all, the fact that it's slightly off center. It's still basically an inverted V. Inverted V antennas, by the way, are always horizontally polarized. Even though the legs are coming down at an angle, they are horizontally polarized. Now, the angle of the inverted V is not critical. If we take a fairly broad angle, something like that, we will find that the feed impedance will be around about 65 or 70 ohms. As we make that more acute, the feed impedance will lower. And of course, the feed impedance also is affected by the height above ground. But we do get a sweet spot on an inverted V antenna, and that is when, and this actually is quite an acute angle already, that is when that angle there is 90 degrees. If that's 90 degrees there, the feed impedance comes down very closely to 50 ohms, and we get very good VSWR. But you can take the feed out at a more broader angle, or you can take it into a more acute angle. You really don't need to go, or you shouldn't go more than around about 60 degrees. 60 degrees is quite an acute angle. That's probably less than 60 degrees actually. But anyway, 60 degrees is quite an acute angle. Anything less than that, and you are going to have some problems. What is the difference between a horizontal dipole and an inverted V dipole in terms of its performance? Well, the horizontal dipole, let's say that has a gain. Well, let's say it's got 0 dB gain. I mean, that's really neither here nor there. If we make that into an inverted V, we lose approximately 1 dB. 1 dB of gain. Again, that's neither here nor there. So basically, an inverted V has the same efficiency as a horizontal antenna within 1 dB. But there is actually a hidden gain, Because if you erect a horizontal dipole, it would be nice that it's like that. But of course it never is like that. A horizontal dipole always sags. So you have your support point there and your support point there, and the wire sags because of weight, like that. And there's your coax feed there. So you haven't got a straight dipole. So you lose in height. Now the point of maximum radiation of a dipole is in the centre where you've got maximum current. That's the sweet spot in terms of radiation, and it sags. So if we have an inverted V dipole, even though we're losing about a dB in performance, we've actually got that point there, the point of maximum current, high in the air without any sag. And in fact, what you very often find is that you can actually erect an inverted V dipole slightly higher than you would with a horizontal dipole, because the demand on a central support for an inverted V is not great at all. And in fact, there's no reason why you can't use some of these fiberglass masts to support it and get it up at a reasonable height. So what is a reasonable height? Well, we're taught that a dipole has got a sweet spot of a half wavelength above ground. That's the sweet spot. Now, a half wave above ground on 20 metres is 33 feet. That's well within a lot of people's capability. Even in a smallish garden, you could probably get up to 33 feet on the 20 metre band. But when we come to the lower frequencies, such as 7 megahertz or the 40 metre band, we're talking about 66 feet. There's not that many people that can actually erect a 66-foot mast in their garden. So, although we might achieve the sweet spot of a half wave above ground on 20 metres, we are not going to achieve that sweet spot on the 40 metre band. Now here's a classic ESNEC software modelling program showing the radiation angle of a half wave dipole as an inverted V, and you'll see that we've got a point of maximum radiation at around about 30 degrees above the horizon. We've still got pretty good radiation down to 15 degrees, and even a bit lower. You can see that the 5 dB point, the minus 5 dB point, still gives us reasonable radiation at a low angle. So that means to say that the inverted V at halfway above ground is not a bad antenna for DX working. Now I put up on the screen the radiation pattern for an inverted V at a quarter wave above ground, which on 40 metres would be around about 30 feet. And as expected, we see a lot of high angle radiation. That would be ideal for short skip communication on 20 metres or 40 metres. And we get NVIS possibilities, near vertical incident sky wave, which in layman's terms means to say that you can work over short distances with very good signals. But there's also something interesting. If you go to the angle of around about 20-25 degrees, you'll find that we're no more than about 5 dB down. That 5 dB down could quite easily be recovered by adding a linear amplifier, which will typically give us at least 6 dB of gain if we are running 400 watts compared with a 100 watt transceiver. So we can actually recover that lost gain that we would have had on a half wave antenna above ground by adding a linear amplifier. And in actual fact, that antenna is not a bad antenna, because if we add the linear amplifier, we've got the good a good high angle radiation, which is great for short range communication. And we've also got some pretty useful low angle radiation, albeit at about 20 degrees or so.
Now, two interesting points arise from this. First of all, the angle of radiation of 20 degrees. Some would say, well, it's okay, but it's not okay for DX. Because the Flat Earth Society would say that you need 5 degrees, because 5 degrees will get you really a long way. It'll get you right round the other side of the world. Well, in fact, it won't. Now, first of all, you have to understand that DX propagation is not single hop, it's multi-hop. Therefore, you can get DX communication with angles of 20 degrees, perhaps 15 degrees, perhaps 25 degrees. I regularly work across to the States on 40 metres with an antenna that is about a quarter wave above ground, in fact slightly less than a quarter wave above the ground. At that height, there's not great low angle radiation, but there is reasonable radiation at an angle of around about 20-25 degrees, because to get across the Atlantic on 40 metres, or any other frequency come to that, you're going to have multi-hop propagation. Therefore, we don't need 5 degrees. We can do it quite happily with 20 degrees or so. But the other important thing is that, and I've covered this before, the Brewster angle. There is very, very little radiation from a typical antenna in a back garden at 5 degrees. In fact, I would say there's no radiation at 5 degrees of any use. You may be able to measure it close in, but there's no far field radiation at 5 degrees. And even 10 degrees is debatable. And if I will come back to this subject, I found a very interesting paper on the Brewster angle, which shows beyond doubt that you're not going to get any 5 degree angle radiation from a typical back garden. And you'll probably struggle even in an open field, basically because of the Earth reflection cancels out low angle radiation. And this, unfortunately, is never shown on any of the, well, certainly not any of the freebie modelling programs. They are renowned for having very poor modelling capabilities when it comes to ground losses and so forth. So, the good news is, of course, that an inverted V is a very effective antenna. Even at fairly low heights, it's still capable of DX when the bands are open. Now let me finally give you even more encouragement. Bear in mind that I'm using a half-size G5RV antenna at the moment. Alright, it's horizontal, but I could use it as an inverted V, and in fact I may well use it as an inverted V later on to get the height up. But a half-size G5RV on 40 metres is not quite a half wavelength on 40 metres because the centre part is folded down. And it's a quarter wave, or just less than a quarter wave above ground. So it's got everything going against it. It's got no 5 degree angle radiation. It's got lots of high angle radiation. And yet I am regularly working VK and ZL on 40 metres, and in the other evening, or the other morning actually, I got 5 and 9 from New Zealand ZL on an antenna that is only a quarter wave above ground. The reason is quite simply that DX uses multi-hop propagation, and part of the skill of working DX is knowing when to get on the band. And on 40 metres it works very well if you use the grey line propagation. That means to say that you've got sunrise or near sunrise at one point and near sunset at the far point, and that gives you very good propagation. So if you want to work DX and you think that you can't because you can't get your antenna up high enough, take heart. You can. It needs a bit of skill. I'll try and remember to put the link to the grey line propagation indicator below this video. You don't need really low angle radiation, and in fact it won't exist in your antenna despite what others may claim. I've seen it even in magazines that talk about this 5-degree angle of radiation. It's so misleading. I don't know why. Perhaps it's through lack of information. I don't know. There we are. I hope this has been informative to you, and I hope that if you're thinking about an inverted V, it'll encourage you to get outside and give it a try. It certainly is a very capable antenna. You can get the centre high up where point of maximum radiation is, and I hope I've proved to you that you don't need ultra low angle radiation in order to work DX. Setting it up is very simple. You just adjust it for minimum VSWR. I gave a formula of 468 divided by megahertz to give you the resulting feet. Make it slightly longer than that, although in actual fact you very often find that an inverted V is slightly shorter. But it depends on where the ends are above ground. Now, you really want to get the ends several feet above the ground. Two reasons. First of all, for safety reason, and secondly, if you have the ends very close to the ground, then adjusting the antenna is very twitchy. So get them several feet above the ground, say sort of 4 or 5 feet above the ground, or a bit more if you can. Make sure that people can't touch it, and then you'll have no problems in getting a decent VSWR on the antenna. Thanks for the support that you give us on this channel and also at the shop, much appreciated. Don't forget to check our blog, which I described at the beginning of this video. And don't forget to subscribe to this channel. It doesn't cost you anything, but it does alert you when the next video comes up, or when every video comes up. And I try to do one at least once a week. So, you enjoy your ham radio, you take care, thanks for watching, and I look forward to seeing you in the next video. Bye for now.